Here we go with the sample problems for class 5 of Math 117. There are 4 of these. The 4th one is a rather long proof, and I'm putting it in its own recording. So I'm just going to do 1 through 3. Problem 1 actually introduces most of the techniques that are going to be used in the proof. You'll recall that the Borel sigma field is the smallest sigma field that includes all open intervals that extend from real number A to real number B, but included in that Borel sigma field are intervals that are closed rather than open, and intervals whose endpoints are irrational as well as rational. So what I'm going to try to do is to generate the interval that is open at the left end, extends from 1 up to pi, and furthermore is closed at the right end. And I'm going to do that by starting out only with intervals that extend from minus infinity up to some rational number q. So this is a countable collection of intervals, but I'm going to be able to make something much more general out of them. How do I do this? Well, the first thing I'm going to do is to invent an increasing sequence of rational numbers, Q1, Q2, Q3, and so on, that converges to pi. The obvious way to do this is to use successively more precise decimal approximations. Add one more correct decimal digit each time, and that clearly converges to pi. Okay, there are only countably many of those, and therefore I can take the union, and I'm still in the sigma field, the union from n equals 1 to infinity of this collection of intervals is exactly what I want. It's the open interval from minus infinity up to pi. Why up to pi? Because this sequence converges to pi, so any number that is less than pi is going to be in this union. Why is the interval open? Well, all these numbers are less than pi. The sequence merely converges to pi, and therefore pi itself is not in the interval. You have already proved that a sigma field is closed under countable intersections, and that's the trick we need in order to make the interval closed. So let's consider the intersection from n equals 1 to infinity. And let's make the interval be closed and still have pi as its right endpoint. If I can make the interval that goes from minus infinity to pi, I can also make the interval that goes from minus infinity to pi plus 1 over n. And what is this? It's the interval from minus infinity to pi, but it's now the closed interval. Why? Because clearly each of these contains pi, and therefore so does their intersection. But if I consider any number that's a little bit bigger than pi, sooner or later n is going to get so large that that number is not included in this interval, so it's not included in the intersection. And I can do exactly the same thing, of course, with 1 instead of pi. Now what else can we do in a sigma field? Well, we can form complements. So, what I will do is take the interval from minus infinity to pi and form its intersection with the complement of the closed interval from minus infinity to 1. These are numbers with the property that x is strictly greater than 1. These are numbers with the property that x is less than or equal to pi, and therefore the intersection of those two sets is the set of numbers that are greater than 1 and less than or equal to pi, exactly the half-open, half-closed interval that I wanted. In the next problem, we're imagining a very simple game where you roll a die and get paid something. And let me write the payoff as the sum of 3 indicator functions to illustrate the rules of the game. You get $1 if the roll is an odd number. And the indicator function for 1, 3, 5 has the value 1 if the die roll is one of the odd numbers. You get $10 if the roll is an even number. So I take the indicator function for the even numbers and multiply it by 10. So this takes care of the odd numbers. This takes care of the even numbers. And then there's a bonus of $5 if the number is greater than 3. So I'll make the indicator function for 4, 5, and 6 and multiply it by 5. So that's a nice way of expressing this simple random variable x as a sum of indicator functions. But these are not indicator functions for disjoint sets. They're not indicator functions for a partition of the set 1 through 6. In order to move in that direction, what I'm going to do is to define an equivalence relation. X and y are in the same equivalence class if and only if the rolls have the same payoff. So, for example, one of these equivalence classes consists of 1 and 3 because the payoff is 1. The only way to get a payoff of 10 is to roll a 2. If I roll a large even number, 4 or 6, the payoff is 15. And finally, if I roll a 5, I get $1 for odd plus $5 for large, and the payoff is 6. So now I can rewrite x. I can say that x is a sum of indicator functions, one for each set in this partition. The indicator function for 1, 3 plus 10 times the indicator function for the set consisting just of 2 plus 15 times the indicator function for 4, 6, plus finally 6 times the indicator function for 5. Once you see this, it's obvious, but it's a very nice thing to know. For any simple random variable like this, you can always write the random variable as a sum of multiples of indicator functions for the sets in a partition of the sample space. And remarkably, that can work even when the sample space is uncountably infinite, like, for example, the real numbers. So let's move on to problem 3. Very similar to problem 2, only now the sample space is R. And we're playing a game where the payoff is $3 if the random number is in between 0 and 6, minus $5 if it's between 4 and 8, plus $2 if it's between 5 and 7. And what I want to do is, again, to write this as a sum of indicator functions for sets in a partition. The secret of doing this, in my opinion, is to draw a nice graph. And I'm going to try to do it by taking a sheet where the graph is already drawn and writing over it on the tablet. First, I can see that x is going to change value at the endpoints of these various intervals. It's going to change value at 0, 4, 5, 6, 7, and 8. Okay, there's my horizontal axis. There's my vertical axis. Why isn't my vertical axis showing up? There it is. Okay. So, as long as the real number is less than 0, my payoff is 0. But as soon as we get up to 0, the payoff increases to plus 3, and it stays at plus 3 until I reach the value 4. At 4, this penalty of 5 kicks in, dropping the payoff down to minus 2. So from 4 up to, but not including 5, I have a payoff of minus 2. At 5, the third term starts to make a difference. I'm now in between 5 and 7. That adds on 2, which in between 5 and 6 has the effect of bringing the payoff back to 0. But what it does between 6 and 7 is drop the payoff down to negative 3. And that happens only when x is greater than 6 and less than 7. Finally, once I get a value that's greater than 7, only the last term matters. I get a payoff of negative 5, and that will happen for values starting at 7 and going up to and including 8. And as soon as the number is greater than 8, my payoff has gone to 0. So you now see that this capital X is a simple random variable, takes on only 5 different values, And each of these level sets is a Borel set. It's a union of intervals. They may be open or closed. And let's write out what they are now. For function value 0, the subset of R is all the negative numbers union with the closed interval from 5 to 6, for which I get 0, union with all the numbers that are greater than 8, for which again my payoff is 0. And this is the set that belongs in the partition, not its individual components, because all I know is the payoff. I can't distinguish whether I got 0 because the number was negative, because it was greater than 8, or because it was in between 5 and 6. Then I've got 4 other values. I get the value 3 from the interval from 0 to 4. That's a Borel set. I get the value -2 from the interval from 4 to 5, another Borel set. I get the value -3 for the open interval from 6 to 7. And finally, I get the value -5 for the closed interval from 7 to 8. The union of all these intervals is all the real numbers, and these sets are disjoint, so they form a partition. And you can see that, kind of remarkably, I get the same thing that happened in the previous problem. In spite of the fact that the sample space is uncountably infinite, I'm able to write my random variable as a sum of multiples of a finite number of indicator functions. The proof itself for this class is in a separate video, so here is where I stop.